Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to solve one design example for compression members. So the statement is design a truss compression member using W section for dead load 110 kN, live load 140 kN and length of member is 3.4 meter and A36 steel. Okay, the first step is to calculate the applied loads. Factored applied load, so 1.2 time dead load plus 1.6 time live load, so it is 365 kilonewton. So after that we need to select the area, or we need to calculate the required area. So for that we need to assume this, or we need to assume the slenderness ratio value. Actually the area required is equal to PU over phi C FCR, and to calculate the phi C FCR we need the slenderness ratio value. So at the initial stage, when we don't have the dimension of the section, so we can assume the slenderness ratio value. So for W section we can assume this slenderness ratio equal to 90, and we need to compare this assumed value with the critical slenderness ratio. And critical slenderness ratio RC in case of A36 steel it is 133. So 90 is less than 133, so it means we have inelastic buckling in our column. So based on this information, as there is inelastic buckling, we can use this expression to calculate the FCR value, and here Fe is equal to pi square E over KL over R square. So after calculating Fe, we can substitute in this expression and we can calculate FCR and multiply it with phi C 0.9 to get phi C FCR. So its value is 146.46 megapascal. So once we have phi C FCR, then it's simple to calculate the required area. So that is simply PU divided by phi C FCR, and PU is 356 kilonewton, and if we multiply it with 1000 to get Newton, so 356,000 Newton divided by 146.46 phi C FCR. So it will give us the required area 2431 millimeter square. So once we have the required area, then the next step is to calculate or to select the section. So to select the section, we need to consider these four guidelines. Area selected should be equal to or nearly equal to area required. We should go for the section with minimum weight, and B of the section should be more than B minimum, or 54, which is 2.5D plus 16. And the depth of the section should be less than 360 for W section. So we will select the section by keeping these four criteria. So here the A required is 2431. So we will go into the properties table, and from there we can select the section. So if I see over here, so here the area of the section, so 2430, so if we see this one, so it is 2860, so it is close to 2430. So we can select this section 150 by 22.8. So there are other options as well. We can, for example, go for this section 200 and 2480. We can also go for 2860. So different options are available. So in this case we are going to select this section W 150 by 22.5. Okay, if once we have selected this section, then we need to note down the properties of that section. So we can select the properties, for example, area of the section, depth of the section 152, width of flange 152, thickness of flange 6.6, thickness of web 5.84, K value 13. We also need, or we can select the BF over 2TF value directly from here. So we can select these two values directly from here. And also we need this RX value 65 and RY value 36.8. So we can summarize this value over here. So here we have section, selected the trial section 150 by 22.5. So here I have enlisted the properties of that section. Area 2860, BF 152, TF 6.6, D 152 and TW 5.84, Rx and Ry and K value. So once we have these information, then we need to perform the checks. So first we need to perform the local instability check. For that, B over T ratio should be less than lambda R. So in case of W section, so this is B over T, but if we consider the full flange width, so it will be B over 2 TF. So B will be the flange width, total flange width. So BF over 2, 152 is the BF value divided by 276. So it should be B minimum. So we need to satisfy this condition as well. B should be greater than B minimum, 54. Okay. So next is lambda BF over 2TF. So its value is 11.5. We can directly select from the table, or we can calculate 76 B152 divided by 2 times TF is 6.6. So it will give us answer 11.5. Okay. So we need to compare this with this lambda R value, and lambda R we can calculate by using this expression. So because it is a flange, so for flanges of the hot rolled section, I section, so we can use this expression to calculate the lambda R, limiting slenderness ratio for cylinder sections. So its value comes out to be 15.8, and 11.5 is less than 15.8, so it means okay, our local instability check is satisfied. Similarly, for web we also need to perform the local instability check. For that, lambda is equal to H over TW. So here we need to calculate H. So H is actually D minus 2 times K. So if we see this figure, so here this K, so actually the section is like this. So instead of this length, we need to consider the H from here up to here. This one will be H, and K is from here up to here. So it is K is more than thickness of flange. So while calculating H, we need to subtract K value instead of thickness of flange. So K value I have already noted, it is 13. So here we can calculate D is 152 minus 2 times 13. So it is 152 minus 26, 6, 3, 136. So H is 136 divided by TW is 5.84. So it will give us 21.6. So this lambda value will be equal to 21.6 here. So we need to compare it with lambda R. So in case of webs, so web of the doubly symmetrical rolled and built up section, so for I section or C section, the lambda R value is given by 1.49 E over Fy. So for this section we use this limiting slenderness ratio for web. So its value comes out to be 42, and the slenderness ratio H over TW for our selected section is 21.6, and it is less than 42.1. So it is okay. So it means local instability checks are satisfied for unstiffened as well as stiffened elements, mean for flange as well as web. Okay, after that we need to perform global instability check. So for that we need to calculate slenderness ratio along the both axes, Rx as well as Ry, or we need to calculate R maximum. So to calculate R maximum, we need to consider the unsupported length divided by R minimum. So if we see here, so Rx is 65 times 10 raised to power 4, and Ry is 36.8 10 raised to power 4. So Ry will be the minimum radius of gyration. So we need to substitute that value. Here it is 37.1, it is actually 36.8. sorry, we need to check the value of ry. Yes, it is 36.8. so here I have written it incorrectly, so this should not be over here. So if I see it again, Rx is 65 and Ry is 36.8. So 65 and 36.8. So here we need to substitute the minimum value, so that is 36.8. So when we will divide 3400 divided by 36.8, it will give us answer close to 90 or 92. So it is less than 200, so it means the global stability check is satisfied. There will not be any global buckling. So now we need to compare our slenderness ratio R with the RC, critical slenderness ratio, to check whether the column is long or intermediate column. So as this value 92 is less than RC 133, so it means there will be inelastic buckling. So we can use this expression to calculate the slenderness, to calculate the FCR value or phi C FCR. So phi C FCR comes out to be 143.66 when we use this expression. And once we have this phi C FCR, then we can calculate the capacity of the section, phi C Pn, which is equal to phi C FCR times area of the section. So it will give us the capacity of section, which is 411 kilonewton, and it is more than 356 kilonewton the applied load. So our section is capable to resist the applied load. So we have satisfied all the three conditions. The local instability checks have been satisfied, the global instability check has been satisfied, and the capacity of the section has been checked, and it is more than the applied load. So it means our selected section is adequate to resist the applied load without any local as well as global instability. So the final selection will be this one.